We continue our investigation of Standard 2.0A.2, fluently add and subtract within 20 using mental strategies. And now we are moving into using those mental strategies with subtraction. As you can probably expect, this tends to lag behind the mental strategies for addition. That's because those addition facts become part of the tools that you can use to help you mentally solve subtraction facts. So emphasizing the addition mental math can also help you towards the goals that you have for mental math with subtraction. Now that is not an obvious leap. Just because they are growing in terms of being able to do mental math with addition doesn't mean that you'll see them applying it for subtraction. They could use some support in that regard. So the purpose of this lesson is to really investigate some of those strategies. This quote is from the Common Core Progressions, as I've referenced that before, and so you probably know that it is written by the Common Core writing team. I strongly recommend these progressions for reading material. They elaborate on the underlying meanings of the standards, and they articulate the focus and coherence elements of the standards. The progressions document that I'm quoting from here comes from the kindergarten through 5th grade operations and algebraic thinking progression. In describing how 2nd grade expectations differ or extend from 1st grade expectations, we find the statement that more 2nd graders master level 3 methods for adding and subtracting numbers within 20. The level 3 methods are not really discussed in the main body of the Common Core standards, but they are in the Common Core progressions. In fact, they're one of the items that are particularly elaborated in the appendix. These methods are to have first been introduced in 1st grade, but they take some time for students to develop a sense of fluidity with which they use them, and so that carries into their 2nd grade expectations. Although the methods are described in more detail, those level 1, 2, and 3 methods are described in more detail in one of the 1st grade PD modules, we're going to take a quick look at what is meant by level 3 methods, and then most of our time together in this lesson will be spent on looking at different ways in which you can apply level 3 methods to subtraction within 20. You might assume if there is a level 3 method that there is probably also a level 1 and level 2 method there somewhere, and there are. Even if that Common Core terminology is unfamiliar to you, I suspect you are familiar with the concept. Level 1 methods are very typical of kindergarten and early 1st graders, and this approach involves acting out problems with each quantity being physically represented through fingers, counters, or drawings. And they essentially use the story to solve the math problem because their mathematical knowledge base is still pretty small, so they use the story and act out the story to get to a solution. As their mathematical relationships grow, they get to the point where they can abstract one quantity and move forward, and so that's evidenced by their emerging strategies for counting on. And so counting on and other counting forward and back methods are level 2 methods. And then level 3 strategies are more advanced, and these are to be actively fostered in 1st and 2nd grades. Level 3 methods involve using a known mathematical concept to convert a hard problem into an easier one. On this slide, you see the characteristics of these methods. As we consider strategies, though, for how to facilitate these level 3 methods, we need to ensure that the strategies that we're featuring really get students thinking about mathematical relationships, using their knowledge of mathematical relationships and the properties of operations, and also choosing strategies that really lend themselves to these unique numbers, noticing things about the numbers that will help them in, rather than choosing some sort of one-size-fits-all method. So let's look at an example to illustrate the relationship between arithmetic strategies and problem solving that occurs during the application of a level 3 method. Here we have a problem. It's a part-whole problem with one part unknown. And as adults, we recognize that to be a subtraction problem, although the second equation, where it's written as a missing addend, is also considered accurate for this situation. I have shown two different level 3 methods here. Both of them involve using the idea of decomposing. Decomposing numbers and taking advantage of our number system is very useful. So we're going to talk about two different ways to do that. In the first example, off to the left, you see that a child decomposes the 8, that's the subtrahend. And so they're decomposing the subtrahend 8 into a 7 and a 1 and then subtracting incrementally. A child who's using this strategy may not show the number bond like I have illustrated it here, but they basically realize that subtracting 8 is the same as subtracting 7 and then subtracting 1 more. And they've used this property and also their capacity to decompose numbers in a variety of ways to easily subtract 17 minus 8. The strategy on the right may be less familiar to you. My younger daughter, who's in Singapore math, has used this strategy fairly frequently. And it is designed to take advantage of the significant work that's been done on building their sums of 10 or their combinations of 10 since kindergarten. So in this case, the 17 is composed into a 10 and a leftover. And another idea that they started working on in kindergarten was this idea of decomposing teen numbers into a 10 and a leftover. So that's also really familiar. And then we have to remove 8, but we can remove the 8 from the 10. That's an easy fact because it uses our sums of 10. There's another kindergarten idea that we first started working on in kindergarten, our sums that make up 10. And then the child takes the result 2 and combines that with the remaining leftover and has 9. It's harder to explain than it is to do, but definitely, and this will become more obvious in the next lesson, all new strategies like this don't get introduced like this. I would never introduce this strategy by showing students this image. We begin with concrete and make sense of it before we start trying to abstract the representations. One of the strategies that I just showed you on the previous slide is called decomposing a number leading to a 10. That's a rather bulky title, so I don't necessarily recommend that you use that title with children. Come up with some more user-friendly label. Because this strategy is named very specifically in the Common Core, we're going to take a closer look at it. 10 is a very useful landmark in the number system, and it comes in handy for both addition and subtraction facts. So since we're talking about subtraction now, let's use a subtraction example. We'll use 13 minus 5 as the top example. The thing that makes 13 minus 5 difficult is that it crosses a decade. But we really can reduce that cognitive difficulty by merely subtracting it in 2 incremental chunks and stopping off at 10. So if I can tell that 13 minus 3 is 10 and that 10 minus 2 is 8, I've just done exactly what 13 minus 5 is. I decompose the 5 into a 3 and a 2 so that I could sort of stop off at 10 as a friendly landmark. So in this derived fact strategy, let's think about what has to be in a student's knowledge base. They have to know how to decompose the subtrahend into some useful parts. It isn't just anything. Notice I didn't do 4 and 1. I did it in 3 and 2. I did that very intentionally to take advantage of 13. So I'm making decisions. How shall I decompose it? I need a 3 so that I can stop off at 10. I'll decompose it into a 3 and a 2. So that the decomposing that students were to have started working on in kindergarten for all numbers up through 5, and then also the sums of 10, and continued to work with in first grade, that really is very advantageous as students start to work with a mental math approach to subtraction in second grade. The second strategy that you see here is a different way that some children may think about decomposing, although in this case the number they're decomposing isn't the subtrahend. The number they're decomposing is actually the answer. They're finding the answer in chunks, and then they're going to recompose the chunk. So there's 2 different kinds of decomposition. Once again, just to reiterate, in the top example, we're decomposing the subtrahend, the amount that we want to remove incrementally or subtract. And in the bottom, we are decomposing our answer. And so in this case, we can actually add up. The bottom example requires that students recognize that 11 minus 8 is searching for the difference between these two numbers. So if you can imagine on a number line where 8 is located and where 11 is located, the difference between those two numbers is one way to think about subtraction. And so in this case, I can think where I am at 8 and work upwards to 11. Well, if I counted up, that'd be counting up by 4. It's not the most efficient approach. But if I use what I know about 10, that's where we get decomposing a number leading to 10. I can easily solve it because I can think 8 to 10 is 2, because I know my sums of 10, and 10 and 11 is 1. And so there you can find the difference is 3. So there's another strategy, way of using decomposing a number leading to 10. Continuing with our discussion of strategies named in the Common Core, we come to this one, which leverages students' knowledge of addition facts. So I told you that the work that they've been doing, trying to build a conceptual understanding of the relationship between addition and subtraction, as well as what the work they've been doing with single-digit fact fluency, can support them here. Since addition fact acquisition then is typically ahead of subtraction fact knowledge, students really benefit by that. They get to bring that in as a strength to support them with their subtraction facts. To do that effectively, they really do have to comprehend, however, that subtraction is a missing add-in problem. If they think of subtraction as synonymous with takeaway, that's a different kind of an interpretation, then they will probably not find this concept useful. But if they can see the relationship between addition and subtraction, and if they recognize that subtraction is essentially searching for the missing number, which when combined with the subtrahend will give you that whole total, then they will be able to make sense of this. Now, they were one of the first grade standards, 1.08.4, is to build this understanding within students, that they will actually understand subtraction as a missing add-end problem. The Common Core authors are very intentional in where they sequence them, and you can see that intentionality in everything we're talking about right now, because all of the skill sets that are being built from kindergarten and first grade feed into the student's capacity to do this. So if your school curriculum is already aligned to Common Core across all grade levels, and the assessment as well, it would be very useful to see whether the students who came in to you had that understanding about subtraction as a missing add-in problem. However, if you want a quick way to assess this, think about this. Can your students take a fact like 13 minus 8 and reword it and say, oh, this means that 8 plus some number equals 13? Are they able to do that without much support? Are they able to do that without just merely mimicking you? When they look at a subtraction equation, are they able to identify which of the quantities in that equation represents the total? Do they recognize, in other words, that 13 is the total and 8 is one part and we're searching for a missing part? If not, these would be some really good areas for you to address in your instruction. If students understand this really well, then every addition fact that has reached fluency becomes a tool by which they can already reach fluency with subtraction merely by thinking, what do I already know about the single-digit fact that goes with it? The first set of facts that you can foster that builds on this idea of a missing add-end problem and just using what you know about your addition fact to solve the subtraction are your anchor facts. Because this fact knowledge was developed first and was emphasized so strongly, students should be ahead of the game on the fluency with these facts above and beyond some of the other facts that still perhaps need to be derived. So the first place where you can really get students thinking about subtraction as a missing add-in and what fact do you know that can help you here are these sums of 10 and doubles. And you'll notice here that I've just turned them into the subtraction version of themselves. So if their anchor facts are fluent, really the real cognitive load is just involved in thinking through that conception of subtraction as a missing add-in situation. And really that is a really wonderful place for them to be cognitively investigating and thinking through and pondering, because that idea relates to the fundamental meaning of subtraction as an operation and its relationship with addition. So it's a wonderful place for them to spend some time in terms of cognitive complexity. Now, the methods that we've described up to this point are really useful for many, many different problems, although the method itself can also be tweaked. You'll notice that when I did 13 minus 5, I intentionally decomposed the 5 to take advantage of what I knew about the number 13. So it isn't a one-size-fits-all type of method. You use the method as a general guide for how to think through a problem, but it still requires you to make decisions. It's not a mindless kind of a task. There are some other, so while those can be used for all facts essentially, there are some special case methods, some things that we can do with a subset of facts that are well worth using and adding to students' repertoire to help them get even faster with their facts, and also to understand some things about our number system a little bit better as well. So all of these here, we're going to discuss them next, and these can also allow students to work more quickly because they are building up their fluency as they notice particular things about specific numbers that can help them out. So when the difference between two numbers is 0, or when the number being subtracted is 0, then we have a unique situation, which makes for a set of really easy facts. So 17 minus 0 on the top, we're subtracting 0. We use the identity property of addition. Subtracting 0 from a number or adding 0 from a number does not change the value of that number. Now, I'm not suggesting that you teach students the name identity property of addition. I'm not suggesting that you get them to define what is the identity property of addition. The Common Core authors are more interested in the concept than in the label. They want students to understand the idea rather than be able to spout a definition to that vocabulary term. So students, what I'm talking about here is really the concept. So they need to know what role the subtracting 0 and adding 0 have. It doesn't change the value. And then in the bottom one, when you're subtracting, when the difference between the two numbers is there is no difference, okay? 17 minus 17, there's no difference between 17 and 17. Then my difference is 0. Now you'll notice that I didn't use minuend, subtrahend, and difference as titles here, and the reason is because we're really building on this idea, how does this relate to addition? So I intentionally used whole minus addend equals addend to draw attention to the relationship between subtraction and addition. Children first start decomposing teen numbers in kindergarten. I'm using the term teen pretty broadly here to refer to all numbers 11 through 19. So we really want them to then start using that. That's another set of facts similar to the anchor facts, which they should have an easy addition fact in mind that's been internalized because they've worked with those facts for so long. And so bringing those in would be another something you can do with mental math strategies fairly early on, and helping them recognize, what do you already know about this that could help you? Level 3 methods are specifically mentioned by the authors in the progressions because they've found that children who are not exposed to strategic development, such as what we're talking about, they tend to stick to level 2 counting methods, and level 2 counting methods are more error prone and they slow kids down. Kids think of them as easier because they know what to do right away. They know how to count. They have to learn how to be strategic. So initially, being strategic feels really slow and painful and definitely not easy to them because they have to make sense, they have to work at it, they have to try to think about mathematical relationships. So the upfront time is greater. But when they learn how to be strategic, they are so much faster than trying to count like 17 minus 8, for example. That's really painful if they're trying to count. There is an exception, however, when level 2 methods are as efficient or probably more efficient than the level 3, and that has to do with when the difference is small. For example, subtracting 1 or 2 or counting back. If you subtract 1 or 2, you can count back, or if the difference between two numbers is within 1 or 2, if you're subtracting a number that's very close to another. So in this case, we see counting back. If we're only subtracting 1 or 2, it's just as easy to count back as to do anything else. So that is also considered fairly efficient, and they should look out for facts where they can do that. Similarly then, if you are subtracting two numbers which are very close in size or in quantity, then you could just as easily count up. So 9 minus 7, I can go 7, 8, 9. So I see that that's 2. If it's 16 and I'm subtracting 15, then I can just determine 15 is the next number down, that's going to be 1. Okay, so in this case, those counting strategies are also considered very efficient. 9 has some very interesting properties due to its proximity to 10, which is really the basis of our entire number system. Now, I've heard this strategy that I'm about to tell you called the 9s trick, and I really dislike that language because it really works on the basis of mathematical relationships, not on the basis of an arbitrary trick. And I don't like to try to even inadvertently send the message to students that math is about tricks. There are real reasons why it works. So math is about relationships. Okay, I'm going to get off my soapbox about that now, but I prefer to call this the subtracting 9 pattern rather than the subtracting 9 trick. Because I want children to really understand what's happening with this, I'm going to make sure that we invest some time in actually modeling it concretely and then building a bridge to the abstract representation. And I'm going to spend more time showing you that in the next lesson where we actually talk about sort of an instructional sequence. And I'll use this as one of the examples of how you can build an instructional sequence to get students to start employing a strategy. Because I think that just hearing about it is hard to understand. So we don't want to tell students this trick. We want them to learn the trick in a way that makes sense to them rather than telling. So I will use that as an example. But essentially what the strategy is, it involves taking 10, subtracting 10, and adding back 1. So you can take any number where you're subtracting 9, subtract 10, add 1, there you are. You're at your answer at that point in time. So we'll take a look at that in the next lesson. Now, as you can see from both last lesson and this lesson, and even last week and this week, because last week we were doing the single-digit fact fluency, the classroom is really a place where it's a breeding ground for arithmetic strategies. You're eagerly seeking it, you're fostering it, you're celebrating it when you see them use it. I want children to understand a repertoire of strategies and have enough time playing around with them that they can add them to their repertoire. However, even though we're featuring and targeting some different strategies so students get a chance to play with it and explore it, make sense of it, and use it, in the end, our goal is that students will have that as just part of a repertoire and they'll make decisions about what strategy do I want to use here. And so in the next lesson, where we talk about instructional techniques, we're going to talk a little bit about how to make that transition to students making the decisions. What strategy might I use here? For these numbers, what strategy lends itself to this? So we'll talk a little bit about that in the next presentation. But their choices shouldn't be arbitrary. They shouldn't be based on tricks. They should be based on a fundamental understanding, because in the Common Core they will have to be able to explain why the strategies work based on mathematics.